All right, our main goal today is to really understand cosets better. And I think this is a good starting point, given a group G and a subgroup H of G, to define an equivalence relation. A is equivalent to B by this condition that A inverse B is in H. How is this related to cosets? We'll come back to that. Let's first go ahead and show this is an equivalence relation on G. So again, it's always nice with your equivalence relations. It goes in alphabetical order, reflexive, symmetric, transitive. So with the reflexive property, reflexive, we want to show any A in G is equivalent to itself. For A to be equivalent to A, that would mean A inverse times A would have to be an H. But that's relatively easy, right? Because that's just E. Since H is a subgroup of G, the identity is in H. And that means A inverse A equals E is an H for any A in G. For all A and G, and therefore that means any A in G is equivalent to itself. Probably would have been better to start that out saying, give me an arbitrary A in G. And then show this. So that verifies the reflexive property for an equivalence relation. What about the symmetric property? Let A and B be in G, and suppose A is equivalent to B, we must show B is also equivalent to A. A being equivalent to B means, again, by definition here, that A inverse B is in H, not G, but H, right? We're talking about relating it to the subgroup H. We know A inverse B would be in G. What do you think is the trick here? It is related to the fact that H is a subgroup of G. Probably shouldn't even call it a trick. What's a fundamental fact you need to use about subgroups here? They are closed under taking inverses. And why is that helpful? Because of sock shoes, A inverse B inverse, you switch around the elements and take each of their inverses. But A inverse inverse is just A. So we've shown that B inverse A is also in H. This all implies B is equivalent to A. So closure under taking inverses. I'll just say closure. Or it's closure under taking inverses. And finally, the transitive property. Let A, B, and C be in G. Suppose A is equivalent to B and B is equivalent to C. We must show A is equivalent to C. These two conditions imply that A inverse B and B inverse C are both in H. Remember, we've got this subgroup H that we relate this to. What's the trick here? Again, it's closure, but now not under taking inverses, under actually multiplying. You've got two things that are in H. H is a subgroup of G. These things imply that their product is in H as well. But what is their product? Their product is A inverse C, right? Because of this trick. And the associative property. Okay. I could see this problem being on an exam 2. It's the type of problem you should be able to do. A little bit of trickery, but once you get in the habit of practicing these things, it's something you should be able to do. So practice it. Go beyond just the homework problems that are due, do the extra practice problems, redo things that we've done in class, rethink about them. It's worth your time. All right, well, what's the big deal about this? Why is this a problem worth thinking about? Again, we're defining A to be equivalent to B by this condition, A inverse B is in H. This is related to a property of cosets. Let's look at the properties of cosets. This big lemma. Lemmas are named lemmas because they're thought of as being what are called helper theorems. So, you've got theorems as being your big important facts. Corollaries are things that follow easily from theorems. Lemmas you think of as being helper facts for doing other things, but these are plenty important in their own right. It's not that a lemma is unimportant. This is a pretty important lemma. Maybe you could say it's the most important lemma in the book. Let H be a subgroup of G, and let A and B belong to G, then all these conditions are true. And the condition that's related to the equivalence relation that we just talked about is condition 6. AH equals BH if and only if, oh yeah, that looks familiar there. A inverse B is in H. Say this in words, just like the author recommends. The left coset of H in G containing A equals the left coset of H in G containing B, if and only if A inverse B is in H. Pretty weird thing to say, but if you're going to really get this, what this is all about, it's worthwhile to focus on saying that kind of thing as you read this. And we are going to think about it intuitively too. And by the way, the roles of A and B are symmetric. You could say this is true if and only if B inverse A is in H. But it is important that the inverse be on the element on the left. That is important, actually. Okay. So, a little funny, but important. All right. How do you think about this intuitively, and why are cosets important? Let's think about cosets intuitively. You've got plenty of examples in the book, and I think at least 1 or 2 examples in the lectures as well. Make sure you think about examples. We did a little bit before spring break. But let's think conceptually about what's going on here and its relationship to Lagrange's theorem as well. So pretend this blob is a group G, okay? And remember, Lagrange's theorem is about finite groups. So let's go ahead and pretend this is a finite group. A finite group. So I could maybe imagine the elements of G not necessarily being this blob, but dots within the blob. I'll go ahead and make a bunch of dots. Those are like the elements of G. Oh, how many of them should I make? How many have I made so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's make 20 total. 13, 14, 15, 16, 17, 18, 19, 20. Okay, so 20 points in G that are, say, the elements of G. G is a finite group of order 20, we can pretend. And we've got some subgroup of G, H. And remember what Lagrange's theorem says. Lagrange's theorem says the order of H must divide the order of G. Lagrange implies that the order of H divides the order of G. And if the order of G is 20, that means the order of H must be either 1, 2, 4, 5, 10, or 20. Let's pretend, just for the sake of the picture, that H has order 4. Maybe it consists of these 4 elements here. Maybe that's H right there. Okay. Well, if H is a subgroup of G, the identity's got to be one of those four elements. Let's pretend that's the identity right there. E. Okay. So there's our setup. How can I think about cosets intuitively in the setup, in particular the properties? Property 1 says A is an element of AH. Well, what is the coset again? We should remind ourselves of that. For an arbitrary A and G, the left coset of H and G containing A, AH or A for fun. Left cosets are A, right cosets are Ha. This thing is AHA. Yeah, although in general, that's not a coset. Unless A happens to be in H. Then it equals H, which is a coset. AH is a set initially. And in fact, remember the book initially defines this purely as a set, not even assuming H is a subgroup of G. This notation means the set of all products of the form A times little h, as little h varies over capital H. That's what, if H is a subgroup of G, is called the left coset of H in G containing A. And why do we say containing A? Because it does contain A. Because if the little h is E, the identity, AE is A. That's a proof of this fact. So every element is in the left coset containing that element. In particular, E is in the left coset of H and G containing E. And in fact, EH equals H itself. E is in H. That's the left coset of H and G containing E. It does equal H because if you consider all products E times H, as little h varies over capital H, you get those same little h's back. But if this coset truly has more than just one element in it, as I pictured it to, let's go ahead and give those elements names. I could use subscripts A1, A2, A3. Maybe I'll use just letters A, B, and C. A, B, and C say, okay, here's an arbitrary A and G, but this is a particular A and G. In this picture, you could also write AH equals H, BH equals H, and CH equals H. Again, this A here is not an arbitrary element of G. It's this particular element right there that I'm pretending is that point. Those left cosets are all the same. They're all equal to H. These four elements, E, A, B, and C, are all in H. They're all in the left coset of H in G containing those elements. These equations are all true. They're all the same. But if I move on to some other element that's not an H, say this one right there, call that D, DH does not equal these. But DH does contain D. And moreover, by this property, property 7, it's going to have the same number of elements as H, in fact, 4 in this picture. Or maybe it contains these 4 elements here. So that we could pretend is DH. And if I give names to these other 3 elements that are in DH, I could represent the coset other words. Should I go ahead and do that? Okay, I don't want to use E, right? Okay, F, little g and little h. Okay. Maybe that's not such great notation because little h is not in capital H there, but dh equals fh equals gh equals hh, where this h happens to not be in capital H. That's another coset, a separate coset. And in fact, it's got no overlap with the first coset. Property 5 says, given two arbitrary elements A and B, the left coset of H and G containing A and the left coset of H and G containing B are either equal to each other or they are non-overlapping, disjoint. Their intersection is the empty set. That's the empty set there, not a phi. EH, AH, BH, and CH are all the same. They're all the same set. In fact, they all equal H. DH, FH, GH, and HH all equal each other as well. And there's no overlap between these two sets. Their intersection is empty. And I could continue doing this. And what am I really doing here when I might continue making this picture? Related to something in chapter 0 and related to your participation for today. What am I doing? What's that called? Starts with a P. Go ahead. It's a partition. I'm breaking G up into pieces. I'm partitioning it. That's what equivalence relations do, right? This equivalence relation that we're talking about here, well, it is an equivalence relation, so it generates a partition. But there's nothing about cosets here. By property 6, I could have written it in terms of cosets. I could have said A is equivalent to B if AH equals BH. I could have written it that way. And the partition that this equivalence relation generates is exactly this one that I'm picturing here. And what do you know about equivalence relations and partitions? Partitions break up a set into, in this case, finitely many pieces. It actually can be infinitely many pieces if your set is infinite, that are non-overlapping. The intersection of any two of them is empty. They are disjoint, and their union is the entire set. Moreover, here, with this particular partition, property 7 says each set has the same order. Actually, in general set theory, you'd call it the same cardinality is the word to use. Same number of elements. That doesn't happen in general for arbitrary partitions, but it is here in a finite group, where the partitions are defined by left cosets. And the proof of Lagrange's theorem follows pretty easily from this, because G is the union of disjoint sets that each have the same number of elements, finitely many of them. The order of G is going to be divisible by the order of any of those sets, which is the same as the order of H, the same as the order of the subgroup. Have I put the proof of Lagrange's theorem on test before? I think I actually have. It's not super hard. Maybe a little bit awkward to state, but you should study it. Could show up on the exam. It's a foundational fact of finite group theory. You could say it's the most important foundational fact in finite group theory. That's maybe unexpected, a little bit surprising, though once you've done enough examples, it's not too surprising. And Its proof, amazingly, is not too hard, though it is related to the idea of a coset. Let's continue thinking about this lemma some more. Make sure these are the kinds of things that you want to kind of get in your soul. And you remember in linear algebra, you had the invertible matrix theorem that ultimately had like 20 parts to it, right? Equivalence conditions for a square matrix to be invertible. What are some of the conditions? The determinant is non-zero is the one that pops to mind most immediately. The columns form a linearly independent set. The rows do as well. They also form a spanning set if it's an n by n matrix, spanning set for Rn, which means they're also a basis of Rn. Words from nightmares. Linear independent, spanning basis. We actually do come back to those words later in this class in about a month and a half or so. We do talk a little linear algebra in here. Bunch of conditions. So pivot in every row related to row operations. It's kind of similar, right? Not quite as long, actually. You want to get to the point where these are pretty natural for you to think about. That doesn't come without practice, without spending time reviewing these things. And these could also show up on true, false, or multiple choice questions too. You want to know them that well. And remember, you know no cards on exams here. So this is something to work at. So again, any arbitrary element is in the left coset containing that element. By the way, it would also be in the right coset of H and G containing that element. Ha. Right? Proof is pretty similar. AH equals H if and only if A is in H. We saw that in the picture. You could also say HA equals H if and only if A is in H. This looks kind of like an associativity. This is what is this saying? This is saying the left coset of H in G containing AB is the same. How should I read that? This one's actually a little trickier to read and is more related to the fact that in the initial definition of this notation here, H does not have to be a subgroup. BH is not necessarily a subgroup of G. In fact, it would not be a subgroup if B is not in H. So you really shouldn't call this, as it's written here, a left coset, though it does end up equaling this left coset. So in the end, it is a left coset. BH is just the set of all, well, you could call that a left coset. That's the left coset of H and G containing B. But that in itself is not necessarily a subgroup of G. So it's a little funny to call this a left coset, but because it ultimately equals this, it is in the end a left coset anyway, so it's not really a big deal. Yeah, it is kind of like associative property. You can put the parentheses either spot, which means you can also make sense of these things without parentheses. This is more important than you might imagine. Although it's not there. Okay, there's going to be a property in chapter 9. In chapter 9, we're going to be talking about what are called normal subgroups and what are called factor groups. Okay, the equation I'm about to write down is really not so much of a thing to prove as it is a thing to make sense of. We're going to define what it means to multiply cosets. I'm going to go ahead and write the equation now, but we're not really getting into details. Give me two arbitrary cosets, AH and BH. What does it mean to multiply them? That's what we're going to explore in chapter 9, and I'm only just alluding to right now. It means essentially to create a new coset where you multiply the A and the B. By the way, the A and the B in front of these H's are called the representatives of the coset. Just like in a partition, equivalence classes, you can have representatives, same idea. Back over here in this picture, E, A, B, and C are all representatives of the same coset. If we were using equivalence class notation, we would write the equality between all these as like this, right? Remember this notation? If we were using general equivalence class notation, we'd write that instead of using coset notation. But it'd be the same idea. They all represent the same equivalence class. The cosets are the equivalence classes. Anyway, we're going to define what it means in chapter 9 to multiply left cosets. This is not a fact to prove. It's more something to make sense out of. Does this make sense? It's called well-defined. Is it well-defined? If you had different representatives of these cosets, would you get the same thing? Is the issue. This is a big issue. And the answer is, it depends. Sometimes it makes sense and sometimes it doesn't. It depends on H being what's called a normal subgroup. If it is a normal subgroup, then it makes sense. If it's a non-normal, abnormal subgroup, then it doesn't make sense. So normal subgroups are special kinds of subgroups. We're not getting into it right now, other than to relate it to one more thing in here. Okay, I guess I am kind of getting into it. Property 8 is related to normal subgroups. A equals ha, if and only if H equals aha. AH equals HA, the left coset of H and G containing A equals the right coset of H and G containing A. They're the same set. They both always contain A. The question is, are all their elements the same or not? Well, that's going to happen if and only if this is true. Where what's that thing? What's aha? That's not a coset in general. This is the set of all products that look like this as H ranges over capital H. That's not a coset in general unless A happens to be in H. It's called you could call it a conjugate of H. It will always be a subgroup of G. In fact, I've sometimes put the proof of that on tests. Prove that the conjugate of H, this particular conjugate, there are other conjugates if you use different A's, is always a subgroup of G. You can just use a subgroup test. Is that hard? Let's think about it briefly. It's always a subgroup of G. We're doing some pretty abstract stuff today, aren't we, right? So we usually focus on examples in class. Well, I guess we've been doing really abstract stuff recently. I think it's worthwhile to do really abstract stuff. This is worth your while to think about, okay? Because you got to struggle with it at some point. Got to wrestle with it at some point. Is this always a subgroup of G? Well, first, is it non-empty? Does it contain the identity? Yeah, take little h to be the identity. I'm assuming H is a subgroup of G here. Take little h to be the identity. A inverse is A inverse is E. In other words, E can be written in this form. And that's an element of H because H is a subgroup. Therefore, E is in here. This does contain the identity. Is it closed under Multiplication. Yep, that's not too hard. Give me two arbitrary elements in there. What happens when you multiply them? By the associative property, you can write this. That is the identity. So ultimately it simplifies to this. And this is in capital H, since capital H is a subgroup. So this product is in the conjugate. And is it closed under taking inverses? Well, take an inverse of an arbitrary element. There is an extension of the sock-shoes property. So when you have the product of three things, I guess instead of calling it the sock-shoes property, you call it the what? Socks, shoes, boots property. First put your socks on, then your boots, or then your shoes, then your boots. And to take them off, you got to take your boots off first, then your shoes, then your socks. You reverse the order of all these and invert them all. And since A inverse inverse is A, you do get something of the form A times something in capital H times A inverse. This thing is in capital H. And therefore, this whole thing is in this conjugate. It's hard to get your mind around this without examples, isn't it? Work at it. Work at it. So, quick verification. I put this kind of proofs on tests before. I think I typically put it on exam 1, actually, so we're already past exam 1. That conjugates of a subgroup are also subgroups, meaning in general, they're not cosets, because cosets are not usually subgroups. Given H, a subgroup of G, only one coset is an actual subgroup, H itself. The other cosets, these other things don't even contain E, they can't be subgroups. In general, this thing's not a coset unless A happens to be in H, in which case it equals H, which is the condition here. Which is a subgroup. And that's the conjugate is always going to give you H whenever the left and right cosets are the same, is what this is saying. And this is surprisingly important, okay? It's important for chapter 9 for when this condition makes sense. Because H is going to be normal in G if and only if this is true, no matter what A is. Besides being abstract, this is a lot to take in, isn't it? Right? It's a lot to try to imagine yourself remembering. You got to work at it. 9 just re-emphasizes things I've said. H is a subgroup of G if and only if A is an H. Like I've said, you want to get these things in your soul, deep down, to try to work at remembering them, to have them make even some intuitive sense. Can you make some intuitive sense out of this one? Number 6, which is related to your class participation again. Is there a way to make intuitive sense out of that? Yeah, there actually is. If you're thinking about these cosets being equal, A and B are elements of G. H is a subgroup of G. It's not an element of G, but it's kind of like you're multiplying things here. A times H and B times H. Kind of. And can we, for example, left multiply both sides by A inverse? Well, maybe. And if we could, I guess property 3 would say I can change where the parentheses are. like this. And hey, A inverse A is E. And EH does equal H because E is in H. This kind of hand-wavy calculation, I'm not being really rigorous here. I'm just sort of saying, let's pretend these kind of calculations make sense, are saying ultimately that the equality of these left cosets must be equivalent to the equality of H with this left coset. And that is equivalent to A inverse B being an H, which is what property 6 says. I don't think I do this in the lectures until ring theory, but it's fun to think about this property 2 in terms of a giant slurping sound. What do I mean by that? It's like A gets sucked into H. The left coset of H and G containing A is the same as H. A gets sucked into it, disappears, if and only if A actually is in H. So it should get sucked into it. A inverse B is getting sucked into H here. Okay. Are you having fun? Right, you have to humor yourself in some way with all this stuff. Don't make giant slurping sounds during the exam. You're going to have to spend time rethinking about this stuff, or maybe thinking about it for the first time if you've not been paying good attention here today. And yes, it is relevant for Lagrange's theorem, and yes, it is relevant for normal subgroups and factor groups in chapter 9, which is super important as well. Factor groups are very important in studying groups. And what was our goal with group theory? What is our goal with group theory? Our goal with group theory, especially finite group theory, is to classify groups. In chapter 7, we start doing that as corollaries of Lagrange's theorem. What's one corollary? Corollary 3, every group of prime order is isomorphic to ZP. Every group of prime order is cyclic. Whoa, no other possibilities. That's pretty mind-blowing if you think about it. Give me a group of order. What's an example of a big prime number? It's 91 prime. Give me a group of order 91. Hey, 91's prime, it's cyclic. Done. It's classified. I hope I got that right. 91 is prime, right? I'm forgetting. I think so. 97 also prime, I think. Give me a group of order 97. Bang, it's cyclic. I've classified it. Nothing more to be said. Whoa, does that seem too easy? And by the way, why is this true? Proof. Suppose G has prime order. So G is a group with a prime order. Let A, B, and G. What would be the goal of trying to prove this? To try to prove G is cyclic, I guess you'd have to come up with a generator of G, right? If A was equal to the identity, then it would not be a generator. So I guess A should not be the identity. Maybe any non-identity element is a generator. And yeah, that's true. Give me some non-identity element. Lagrange's theorem implies the order of A is the same as the order of the cyclic subgroup generated by A must divide the prime P. Well, there's only two possibilities, 1 and P. P is prime. If A is not the identity, it doesn't have order 1. So it must have order P. Done. it's got to be a generator. G must be cyclic. Earth-shattering fact proved in 2 sentences, 3 sentences. Really, it's a one. You could really make it a 1-sentence proof. It's so trivial. It's a trivial consequence of Lagrange's theorem. There's another classification fact in chapter 7, though its proof is harder. Let G be a group of order 2p where p is prime, a prime greater than 2. Then G is either isomorphic to Z sub 2p, cyclic with order 2p, or dp, the dihedral group of order 2p. The subscript there is not a 2p, it's just a p, but it's got order 2p, right? Because it's the symmetries of a regular p-gon with p sides to it, which would include p rotations and then p reflections. So it's got 2p elements. What if p were equal to 2 here, by the way? Well, there's no such thing as a 2-gon, right? So dp only makes sense when p is 3 or greater. That's why this is not. You can still classify groups of order 4, 2 times 2. That's done in chapter 8, in fact. As an example, but it really is a theorem. A group of order 4 is isomorphic either to Z4 or what's that? We haven't talked about that yet. Proof of this is harder, but understandable if you also believe this theorem here. This theorem's pretty useful. Its proof is tricky. Maybe not completely clear as you read it, but it's definitely something worth knowing. H and K are 2 finite subgroups of a group. Define this set. Notice they did not call this set a group, because in general, it's not a group. In general, the set of all products H times K is not a subgroup of G. Sometimes it is, but not always. So they didn't call it a group, they call it a set. Does have order that can be found by taking the order of H times the order of K and dividing by the order of H intercept K, which, by the way, should remember the intersection of subgroups is a subgroup. That's been mentioned before. Pretty useful fact, and is used in the proof of this down here, right there. It's not an easy proof, too long to put on a test, but again, something you should work at understanding and being able to explain, maybe do a fill in the blank proof. I don't know that I've ever done that on a test, a fill in the blank proof for this one, but I wouldn't rule it out. It's understandable in pieces, even if you couldn't imagine putting it together yourself. Yes, the fact that the converse of Lagrange's theorem is false is in chapter 7. This is the one I put on exams before, fill in the blank to give out reasons for all these things. So study that. Also study the orbit stabilizer theorem. I have not had time for that in class, but it is in the lectures, it is in the book. There are examples. You should study that, and you should even study its proof and be able to reproduce parts of the proof. This just seems like a lot to ask, but if you put the time in, you can do it. People do have success when they put the time in.